of the sampling frequency, the component, the copy which is brought to that multiple of the sampling frequency is modified in amplitude and phase by the Fourier series term falling on that multiple of the sample. Okay, so that means typically what would happen is the Fourier series terms would decay as you go away from 0. So you would find the copies also decay in amplitude, and of course would also undergo a change of phase. And what is more is, it depends on, now there are two ways of doing it. One way is you just gate the signal for some time. There is a subtle difference between these two things. You just allow the signal to pass for a small interval of time and then chop it away. That is one way to do this. The other way is not to gate it, but to capture the value of the signal at a point in time and hold it for a short while. Now, there is a very fundamental difference in the way you analyze these two, and as is my habit, I shall leave the difference to you as a challenge. How do you distinguish the two cases in the spectral domain? My answer is, I will give you a brief answer to the question. The brief answer is, when you gate it, that means when you allow it to pass for a short interval and then stop it, then you do exactly what I said a couple of minutes ago. You just multiply the copies by the Fourier series component. But when you hold, when you sample and hold, then you have trouble, because not only are you multiplying the copy, you are also distorting that copy. You are also distorting that copy by the spectrum of the pulse. Okay? So, I leave this to you as a challenge. Suppose I were to do these two different things, how would they differ in what happens on the frequency axis? So, it would need to be analyzed based on a basic exposure to signals and system. But anyway, I am not expecting that I am not thinking of it as a part of the syllabus, but since somebody posed the question, I put this to you as a challenge with this hint. Yes. By the way, I encourage students to write down their attempts to the challenging problems and submit them. Oral discussions are all right, but I give credit when the solution is written down reasonably and submitted. Is that right? Yes. Maybe we can take just one question if there is any other, and then we will continue with our discussion. Yes? Yes. Any other question? You have a question. Okay.
Suppose, sir, if the sample is 0.7 kilohertz bandwidth, 1.4 kilohertz sampling frequency, 0.7 and the original signal will have the opposite phases. So, will it mean that that will be totally cancelled?
Okay. So, the question is, suppose I took a 0.7 kilohertz sinusoid and sampled it at 1.4 kilohertz. Then the first mirror image would be at 1.4 minus 0.7. So, the original signal and the mirror image overlap and with opposite phase, right, and therefore, we expect them to cancel. That is what very often happens, they cancel. In fact, they cancel depending on where you sample, and in fact, this is easier understood in the time domain. Suppose I were to take a sinusoid. Now, when you say that the sinusoid has a frequency of 0.7 kilohertz and you are sampling at 1.4 kilohertz, another way to interpret this is that you have a sampling rate twice of the frequency. In other words, in every period you would have two samples. Now, the original spectral component, sinusoidal component and the mirror image would cancel one another if you sampled here. It would give you all 0 samples. On the other hand, if you were to sample here, they would not cancel one another. So, it is not obvious that they would cancel one another, it would depend on the point of sampling. But there is a potential problem of their cancelling one another if you happen to begin the sampling from a 0 crossing. Okay. All right. Now, that was several questions. We can of course encourage more questions in subsequent lectures, and not only in subsequent lectures, in this lecture as well as we proceed. So, from now onwards, it should be made. Now, I was very happy that we had several questions come up from the class. In future too, we must make this course a dialogue and not a monologue, as I have told you in the first lecture. We insist and we think it is very important that you should participate wholeheartedly in the discussion, for otherwise the classroom would not be as effective as it should. So, we shall make this practice. So, whenever you have a question, you do not have to wait until I explicitly invite questions. Whenever there is a question in between, you must raise your hand and we shall attend to that question and decide how to deal with it at that point in time. Now, we will proceed then with a discussion of what we are just beginning on, what we just embarked on in the previous lecture, namely the question of discrete systems. Now, we will review once again what we mean by a discrete system. A discrete system is a system where you have a sampled input. And a sampled output is produced. We had agreed to call this input x of n and output y of n, and we associated n with the sampling index. In other words, when we say n equal to 0, we mean the 0th sample. When we say n equal to -1, we mean the sample, the -1th sample, or the sample at t equal to minus capital T, and so on, right? And we of course agree that the sampling instants are the same at the input and the output. What we also agreed is our whole objective here is to see, at least in a major part of the course, if I can achieve from a configuration like this what I might with an analog system where you have a continuous input and a continuous output. Hopefully the continuous input is band limited. So, when I sample it, I have sampled it sufficiently so that there is no aliasing, and then I am doing something to the sample. That is what the discrete system is supposed to be specified, right. I am doing something to those samples and producing a stream of output samples, and the stream of output samples that I am producing should be the same as if I were to sample the output signal from the analog system at the same points. I am hoping to be able to do that. So, I have an analog system where I would take a continuous input and produce a continuous output. I sample the analog input, I do something to these samples, and I produce the same samples as I would if I were to sample the output of the analog system directly at the same points, right. I am hoping to be able to build such systems. And I will soon show, not so soon, it will take a while, but we will see in due course that this is possible. And what is important is that for this to be possible, one of the first things that we need, as we saw, is that when I put a sinusoid into the system, I should get a sinusoid as the output with the same frequency. In fact, we said that quite a number of sessions would be spent on building the properties of a system which ensures this. Now, we will spend a minute in asking why we are so keen to deal with sinusoids. There are several reasons. Sinusoids are natural in electrical engineering in a certain way. They are natural because generation of electrical voltages often takes place with the ideal sinusoid as the pattern that is expected. So, if you think of a generator, and if it were an ideal generator, using the laws of electromagnetic induction, the voltage generated would be sinusoidal. Now, that is a reason pertaining to generation. There are several other reasons why sinusoids are natural in nature. But from a mathematical perspective, sinusoids are one class of waveforms which are analytic. They are probably the smoothest kind of waveforms that you can get, and they are self-replicating under derivatives and integrals and addition. Add two sine waves of the same frequency, we have discussed this, and you get a sine wave of the same frequency. The amplitude and the phase changes. Take a derivative of a sine wave, you get a sine wave of the same frequency. Take the integral, the indefinite integral of a sine wave, you get a sine wave of the same frequency. Why are integrals, derivatives and sums so important? Because if I have an electrical circuit, or if I have several different combinations of elements, I often need to do that. I need to add the quantities associated with each of the elements individually. Very often the relationships that govern an element involve derivatives or integrals. For example, an inductor relates the voltage and current through a derivative. Same is true for a capacitor. So, the derivative of the integral is often ubiquitous in several systems, it occurs very frequently, and therefore, it is a good idea to see if you can have a waveform which remains as it is in form as it goes through different kinds of operations. The sine wave is a good answer. A more general answer is what is called the exponential, but we will come to that slowly later. At the moment, the sine wave is a good candidate, and therefore, we would like to deal with sine waves in a decoupled way, right. So, let us put that down. Yes, there is a question.
For sine waves,
yes.
By definition, analytic means the negative frequencies to be 0.
Well, the question is, sine waves are analytic, but then, we talk about negative. Now, let me postpone the answer to this question. I think there is a confusion in this question. The question was that negative frequencies should be 0. Here we are not talking about positive or negative frequencies at all at the moment, right. So, let us not bring in that point in the discussion at all at the moment. It is a little premature. So, yeah, so we wish to decouple dealing with sine waves of different frequencies. What I mean by that is, if I have a discrete system, I give it a sine wave A0 cos. Now, it does not matter whether you write cos or sine. Sampled at t equal to n. So, I get A0 cos omega 0 n plus phi naught. What appears is again A1 cos the same frequency omega naught n, but changed in phase and amplitude. So, the phase and amplitude are changed, but the frequency is unchanged. That is important. So, we are saying two things in one here. We are saying that when I give a sinusoid as the input to the system that I am going to deal with, I need to get a sine wave, point number 1, I need to get a sine wave. Now, that itself is a great thing. If I were to give a sine wave and if I were to get some other kind of wave, I am not happy, right. So, I need to get a sine wave, point number 1. Secondly, I need to get a sine wave of the same frequency, but I am willing to tolerate a change of amplitude and phase. Okay, this is what I want. This is the, simple to say, not so easy to do. To be able to ensure this, now what are the things, what are the obstacles to having this? The first obstacle is that when I put in a sine wave, I may not get a sine wave as the output. The second obstacle is when I put in a sine wave, I may get a sine wave but of a different frequency. There are several obstacles which I may need to deal with. So, it is easier said than done. Ensuring that this happens for all sine waves is indeed a daunting task, and to achieve that I need to put several properties on the system. Now, what I am going to require is something slightly more than this, and we will spend a minute on that. What I am going to require is not just that this hold for sine waves. I am going to require that this hold for something called phasors, and I will now explain that idea in some depth. You see, we would like to think of sinusoids as combinations of rotating complex numbers, and I will explain why. You see, take this very situation here. Let us assume that you are able to do this for whatever reason, right. I am able to get a sine wave of the same frequency and with a possible change of amplitude and phase. Even so, when I take a ratio of the output to the input, the ratio is not a constant. The ratio of course depends on n. In fact, you can write the ratio in a complicated way, right? But the ratio depends on n. What I want to do is to see if I can describe this system at that particular frequency by just a ratio. And what I mean by that is, instead of dealing with sine waves, I need to bring in some other kinds of waveforms, or I need to bring in some other kinds of, now I introduce the word sequences. The sequences are essentially functions of an integer variable, and the physical interpretation of the integer variable is the sampling index. I said functions maybe a little carefully, but we need to qualify whether I am talking about real functions or complex functions. Well, I am going to allow complex functions. And again, the natural question is, what is the physical meaning of a complex functions? If I sample a real signal, I am certainly not going to have complex values. So, where would complex signals come from? Well, complex signals for the moment should be thought of as hypothetical extensions of real signals. So, you could think of them as two real signals, one for the real part and one for the imaginary part. And we will use complex signals as a tool to deal with real signals. For the moment, let us think of it with this reassuring note. So, we do not really have complex signals in nature, but we will allow the sequence to be complex, because sometimes it helps us to deal with real signals by bringing in complex signals for a while, doing some work with the complex signals and going back to the real signal, right. Now, in a minute we are going to use a complex signal. So, you see the complex signal comes in as follows. Suppose I were to take a complex number, rotating a complex number which maintains a magnitude of m, starts with an angle of theta naught and rotates at an angular velocity of omega naught. We know how to write this complex number in polar form. The polar form representation of the complex number is very simple. It is m e raised to the power j theta naught plus omega naught t, right. Of course, this is the continuous complex number. Now, let us assume that I were to sample this complex number with a sampling rate of 1. Okay. I would get m e raised to the power j theta naught plus omega naught times n. You see, all the time I am making the convenient assumption that my sampling interval is unity. Let us get used to this assumption. I mean, I am normalizing my time measurement with respect to the sampling interval. Now, you see, the beauty of this representation is that if I were to change its amplitude or its phase, so if I were to change the amplitude or the phase, initial phase theta naught, right. If I were to change the amplitude, m e raised to the power j omega naught n plus phi naught is of course expressible as m1 by m times e raised to the power j omega naught n plus phi naught. On the other hand, this is of course obvious. So, when I change an amplitude to m1, it is equivalent to multiplying that number by m1 by m, simple enough. But the more interesting thing is the phase. So, if I were to change the phase to theta 1, this could be rewritten as m e raised to the power j omega naught n plus phi 0 plus phi 1 minus phi 0. And of course, that can be rewritten as m e raised to the power j omega naught n plus phi naught e raised to the power j phi 1 minus phi naught. So, in either case you have a multiplying factor here. Whether you take a change of amplitude or a change of phase, it amounts to multiplying the original rotating complex number by a constant, albeit complex. Okay, this is a significant observation. Unlike a sinusoid, where when I change the phase, it is not tantamount, it is not the same thing as multiplying the sine wave by a constant. But in a sine wave, of course, when I multiply the amplitude by, when I change the amplitude, is equivalent to multiplication by a constant. So, therefore, the beauty of dealing with this rotating complex number is that multiplication by a constant factor, albeit complex, is a correct description of change of amplitude and change of phase, and of course, change of amplitude and phase together too. If I change the, and they are independent, if I change the amplitude to m1 and the phase to theta 1 or phi 1, it is equivalent to multiplying by m1 by m e raised to the power j phi 1 minus phi 0. So, you can take them together. That means, when I now put, it is very clear, if I have a system, instead of dealing with sinusoids now, if I were to deal with these, which we will call phasors. So, we call such a rotating complex number a phasor. With a single angular frequency. Let us denote it by omega. Now, why are phasors important to us? The real and imaginary parts of phasors are sinusoids with frequency omega, angular frequency omega. Okay, is that clear? That is straightforward, because we can even write down the real imaginary parts. Indeed, if you have a phasor m e raised to the power j omega naught n plus phi naught, this can be decomposed as m cos omega naught n plus phi naught plus m times j sine omega naught n plus phi naught. This is the real part and this is the imaginary part. Each of them is a sinusoid of the same frequency, omega naught. So, now I see the connection. I also see the advantage of dealing with phasors. You see, what I am going to do is, I am going to think of a sine wave as the real or the imaginary part of a phasor. And instead of dealing with the sine wave, I am going to think that it was the phasor which was applied to the discrete system, and this would result in a phasor coming out with the same frequency, but a possible change of amplitude and phase, right. And the beauty of dealing with the phasor rather than the sine wave is, this process of changing the amplitude and the phase amounts to multiplying that phasor by a complex constant. So, I can represent the action of the system as multiplication by a complex number at that frequency. I want to be able to describe a system like that. Now, this requires some thought. Now, there is another way of looking at it. The other way is, I can think of a sine, of course, I can think of a sine wave as the real or the imaginary part of, but how do I get real or imaginary parts? You see, I must